Hello everyone, myself Kumar Singh and I am the second year BTech student at IIT Roorkee. Today we will be discussing the topic matrix representation of linear transformation and its combination. Let's go ahead. Before going ahead, let's motivate ourselves of why we need to study the linear transformation. If you see, we are using linear transformation in daily life, like image rotating, image scaling, like we are increasing the quality of the images. That's all are uses linear transformation. We can better understanding by this line. Geometry and graphics. Linear transformation are used to perform various computer operations like rotation, scaling, shearing, and translation in computer graphics and the computer aided design. For example, rotating an image or scaling a 3D model involves linear transformation. Before going for better understanding, one thing we can remember is in mathematics, every object is just an matrix, right? Every object is just matrix, just as matrix. So if you translate the object from one position to another position, then we have to just add another matrix with that object matrix with that object matrix another matrix. Then we can translate object from one position to another position. If you want to scale the image or the object, then what we have to do? So we have to multiply with a diagonal matrix, right? Diagonal matrix, if you multiply with diagonal matrix to the object matrix, then that will scale the object. We can see here, this is the scaling in the x direction, this is a scaling in the y direction. This sx is scaling in the x direction, sy is scaling in the y direction. Now, if you want to rotate the object or the image, then we have to multiply with the rotation matrix. Rotation matrix is what? Rotation matrix is a orthogonal matrix. A orthogonal matrix. We can see that this matrix is an orthogonal matrix. The dot product of the column vector is here 0, and so we can say that this is the orthogonal matrix. This multiply with the object matrix, then it will this will rotate the image by angle theta. Now, if you want to share the image, sharing the image, then this diagonal matrix should be 1 and the off diagonal element should not be 0. Then this will share the image, right? This will share the image. One more thing we can understand is reflection of the object, right? Reflection of the object with respect to axis. How we can understand this? Let's understand. We can understand like here, if we have an object, and if we want to reflect this object with respect to x-axis, right? Let's draw it. If you want to reflect this object with respect to x-axis, then we have to here what is the change? Just change it in y direction, right? Y component. If you see here, y is positive, here y is just negative. So we have to multiply just one matrix like 1, 0, and here 0, and here -1. This will change the sign of the y component, right? Y component. If you change the y component sign, then this will be the reflection with respect to x-axis. Now, if you want to reflect with respect to y-axis, then what we have to do? So we have to multiply in x component, right? X component with -1. Here we have to put plus, right? This will do what? This will do reflect with respect to y-axis. Y-axis, this will object will reflect, right? And if you want to reflect with respect to origin, then what we have to do? If you want to object reflect this, then here should be the -1, and here also. If you put -1, then this will reflect the object with respect to origin. Okay. Second usage of linear transformation, we can see it in the data comparison. In data comparison technique like principal component analysis and singular value decomposition, linear transformation are used to reduce the dimensionality of the data while retaining the important information. If you are using the data like in the multiple dimension, right? If you have the data has the multiple dimension, then we cannot visualize that, we cannot draw in the reality. So if we want to visualize that data, then we have to project that data into 2D or the 3D, then we can easily visualize that. But we can think that there is a loss of information, but we are doing this in such a way that we are choosing maximum value of the lambda, so that we have gaining maximum, we have retaining the maximum information, and there is loss of very less loss of information. So we are projecting the data into the 2D and 3D and visualize this, and we are predicted our goal. So right now we are third usage of the linear transformation. We can see it in the signal processing, right? Signal processing, linear transformation are used in the signal processing to filter, transform, and analyze signals. Examples include the Fourier transformation, discrete cosine transformation, and the Wavelet transformation. We can see it by like this, right? We can see here, right? Like can see, understand this. If we have a signal like x of t, and this passes through a system, right? Passes through the system, and this become y of t. And we have also another, this is, let's say, x1, this is x2, and another signal, this also passes through system, and this become y2 of t. This is y1 of t, right? Then addition of these two signals, that will be what? y1 of t plus y2 of t, right? And if we pass it the initial, this initial signal into addition, and then passing through the system, then our result will be same. There will be no change, right? So this is the example of linear transformation in the signal processing. We are passing individually. If you individually passing through the system, then there will be individual result, and adding them or they're finding some another signal, right? Or here adding these two signals initially and passing through the system, then we getting the same signal, right? We are getting same signal. Like this, we are using the linear transformation in many ways. Let's understand the definition of the linear transformation. A linear transformation, often simply called a linear map or the linear operator, is a fundamental concept in the linear algebra. It is a function that maps vector from one vector space to the another while preserving the certain algebraic property. What is that algebraic property? There is two algebraic properties. First is additivity and second is multiplication. They preserve the additivity. How they preserve the additivity? A transformation T is additive if it satisfies the property transformation on the sum of the two vector which is belonging to the vector space, let's say capital V, and transformation on the sum of the two vector. This is the sum of the individually transformation on the these two vector u and v. That is transformation on the u plus v is the transformation of the u plus transformation on the v for all the vectors u and v in the domain of T. Second property is multiplication preservation. A transformation T preserves the scalar multiplication if satisfy the property like transformation on the scalar multiplication of the u is the transformation of the u multiplied by a scalar, right? Multiplied by a scalar. That is, if we use transformation on the c multiplied times u, then this will be equal to the c times of transformation on the u for all vector u and all scalar c. The set of all linear maps from the vector space V to vector space W is denoted by LVW, right? It is denoted by LVW. Example of some linear maps. Here we can see that there is many example of linear maps. So first, let's understand zero linear map. Zero linear map. We can understand map is linear map or the transformation. Linear transformation is just a function. So we are defining zero linear map is as like if we apply zero linear map or zero linear transformation on a vector belonging to vector space V, then it will map to the additive identity element of the vector space W, right? Here it is written, right? We can understand this. The zero on the left side of the equation above is the function from V to W. V to W. This from vector space V to W. This zero is a function or the linear transformation here we are using. This zero means linear transformation. Where a zero on the right side is the additive identity element in the W. This zero is the additive identity element in the W, right? Here we can see the second example of the linear transformation or the linear map is the identity linear map. How the identity linear map is defined is the identity map denoted by I is the function on the sum vector that takes each element to itself, right? That is mapped from itself, from the vector space, and it maps to the itself. Then this map is known as the identity map, right? Is defined by I V is equal to V. And this third, see the example of third linear map is from R3 to R2. Define a linear transformation T from the R3 to R2 by the, let's say, X, Y, Z. Right here, three vector here, where component is X, Y, and Z. Here taking from R3 it's taking a vector V where component is X, Y, Z, and it's giving there is in R2 where component is like this. There is a relation X, Y, Z, there is a relation, and in R2 there is two component, which is first one is this and second one is this, right? In R3 there is vector has three component where each one is what? Each one is X, Y, and Z. Here in R2 there is two vector, there is two component, which is 2x minus one component is 2x minus y plus 3z, and second component is 7x plus 5y minus 6z. This may be a dependent, or this may not be dependent. It's depending on how we are using linear, how we are connecting this, right? Now, one thing we will be proving here is, suppose V1, V2, and the Vn is a basis of a V, and W1, W2, Wn belonging to W, then there exists a unique linear map T from V to W such that TVJ is equal to WJ. How we will prove this? Let's prove this. First, we will show the existence of the linear map T with the desired property, right? With desired property. Here, define the linear transformation T from V vector space V to vector space W by transformation on the C1 V1 plus C2 V2 up to Cn Vn is equal to C1 W1 plus and Cn Wn, right? Where C1, C2, and Cn are the arbitrary elements of the field F, and the list V1, V2 up to Vn is the basis of V. And thus the equation above does indeed define a function T from the V vector space V to vector space W, because each element of V can be uniquely written in the form of C1 V1 plus C2 V2 up to Cn Vn. We can say this where we are telling that V1, V2, and Vn are the basis of the vector space V. Then all the vector in the vector space V can be written as the linear combination of the all these basis vector, right? For each j, taking Cj is equal to 1 and others Cs equal to 0 in the equation above, so that Vj is equal to Wj. If u, v belonging to vector space V with u is equal to a1 v1 plus an vn and v is equal to c1 v1 and cn vn, then transformation on the u plus v is equal to what will be that? U is thus right, u is written, can be written as this. And after, since we are defining, or we are already defined this transformation here, this transformation we already defined, so we can put by here this a1 plus c1 w1 plus a2 c2 w2, and this here using a here we are using distributive property in the opposite direction, right? By this, if we added u plus v, then this can be written as a1 plus c1 multiplication by v1. This all these vector, all their component, that can be written like this. And this here we already defined our linear transformation this, then here we can put like this, and then Then here also we are using distributive property on a1 plus c1 multiplication by w1. W1 here is the vector and a1 c1 is the scalar. So we can use the distributive property, and this will give like this, and this will be the t of u plus t of b. So here we can see that this t of u plus b giving t of u plus t of b. That's implies here this is a linear transformation, right? This is a linear transformation property. Similarly, if lambda belonging to F and vector V is equal to C1 V1 plus C2 V2 and Cn Vn, then transformation on lambda times of V is equal to transformation multiplied by transformation on the lambda C1 V1 plus lambda C2 V2 plus and so on up to lambda Cn Vn. This can be written as similarly from we already defined a transformation. From there, we can write it like this: lambda C1 W1 plus lambda C2 W2 plus lambda Cn Wn. And this can be written again, lambda we will be taking as a common, and this can be written as C1 W1 plus C2 W2 up to Cn Wn. And this is nothing but this is just transformation on the V. That implies this also follow the multiplication preservation. So we are showing that there is two properties, right? Two properties of linear transformation. One is additivity and second is preserving the multiplication. Here the both are satisfying. Thus T is a linear map from V to W. Thus we can say that the here transformation T is a linear map from V to W. To prove uniqueness, now let's prove its uniqueness. Now suppose that a transformation belonging to LVW. We all know that what represent the LVW. This is representing all the linear maps from the vector space B to vector space W. So if this transformation, right, this transformation is belonging to LVW, and that TVJ is equal to WJ or J is equal to 1 to up to N, let's C1, C2 up to N belonging to field F, the homogeneity of the T implies that the T transformation on the Cj Vj is equal to Cj Wj on for J is equal to 1 up to N. The additivity of the T now implies that transformation on the C1 V1 plus C2 V2 up to Cn Vn is equal to C1 W1 plus up to Cn Wn. Thus T is uniquely determined on the span V1 up to Vn by the equation above. Because V1 up to Vn is a basis of V, this implies that T is uniquely determined on V, right? Let's come to our main topic, the matrix of the linear map, right? We will be discussing here the matrix representation of the linear map. That is the matrix from the linear map T. Suppose our linear map T belonging to a set of linear maps which is from vector space V to vector space W, and V1 up to Vn is the basis of the V, and W1 up to Wn is the basis of the W. The matrix of T with respect to these bases is the M by N matrix M of T, whose entries A, J, K are defined by like the transformation on the jth basis vector will be like A1J W1 plus A2J up to W2 up to AMJ Wn, right? Here we can better understand by writing again. Let's write again. So we will be writing like our matrix from the for the transformation T will be like, here we can put the basis vector for the vector space W, right? W1, W2 up to Wn, and here will be V1, V2 up to Vn, and here what element will come? A11, A21 up to AM1. Here what element will come? A12, A22 up to AM2. Similarly, here what element come? A1n, here A2n up to AM. This matrix is the representation of the linear map. We can better understand how we will be getting this matrix by from transformation on vector space B, right? From vector space B to vector space W, how we will be getting this matrix. Let's taking an example and understanding this. Here we have taken an example from the a vector space from R2 to R3 is defined by here transformation from R2 to R3 is defined by like this. Here we are taking a vector from the vector space R2 here there are two components X and Y. we are transforming it into R3, where will be three component. One is x plus 3y, second is 2x plus 5y, and third is 7x plus 9y, right? So we are transforming from what? From the vector space R2 to vector space R3. So by a transformation, this is the function which apply on a vector in the R2 and transforming it a vector in the R3, right? So what matrix, that is what matrix we are applying onto R2, which gives us the a vector in the R3, which matrix? So we are trying to finding that matrix. Find the matrix T with respect to the standard basis. If we have not given any basis, then we have taken a standard basis of the F2 and F3. Let's solution. Here we can take in the R2, what will be the standard basis? One vector will be the 1 0, and second vector will be the 0 1, right? So if we put here at the xy 1 0, then we are getting in the R3 getting a vector which component is 1 2 and 7, right? And putting a basis vector 0 1 0 1, and right, 0 1 in the transformation, we are getting another vector 3 5 9, which is in the R3, right? Again, now what will be the matrix? Here we can see it. We can previously how we were writing. Let's understand this, right? First we have the vector. Here we have the vector v1, v2. v1 is what? v1 is nothing but what? This is the 1 0, and v2 is nothing but what? This is 0 1, right? And we are applying. We have to take a standard basis, right? A standard basis. We are taking a standard basis in v1, v2, 1 0, and 0 1. Also in the vector space W, we have to taken under we have to taken a standard basis, right? So which will be what? 1 0 0, and this will be the 0 1 0, and this will be 0 0 1. And this element, what will be that? So we can see here is what? If we are putting this vector, if we applying transformation on the v1, this was what? This was here multiplying all the element with these basis vector and getting this sum will be getting transformation on the v1. So it implies, if we see here, if we want to find this, right here, if we are putting x y z, then what will be the element t v1, right? t v1, applying transformation on the v1, that will be what? That will be the t1, that will be the what? That will be the a1 here 1 a11 w1 plus a12 w2, right? Here 2 1, here 2 1 w2, and plus up to a m1 w. Here we can see here is what? Transformation on the v1, which is come 1 2 and 7, that will be what? a11. The a11 is we haven't know, that is a11 into w1 is what? 1 0 0, right? Plus a23, a21 is what? We don't know. v21 we will be writing same as 0 1 0, and plus up to, and this is what? This is also a31, we don't know, and this will be writing as 0 0, this will be writing as 0 0 1, right? So here we can see it just as 1 2 7 will be equal to a11 comma a22 comma a31, and we will be taking as we have getting a11 as 1, a21 as 2, a31 is 7. Similarly, we can finding these elements. We can find these elements. putting a transformation on the V2, putting transformation on V2, we will be getting these element, we will be getting these as a result, and we are multiplying these into these into these into the, after summing this, we getting this, we will be getting all these elements, we will be getting all these elements. By this process, we are finding the matrix of the linear map, right? Let's take another example, which is the function or the transformation from R2 to R2 with the f of x, y is equal to 2x, y is a linear map. We all know that already. This function scales x component of the vector by the factor 2. Now, how we will be getting here for this linear map? For this linear map, we will be getting the a matrix. How we will be getting? Let's do it. Here we can see it. We can see here our vector, right? Our is R2. Both are R2, right? If R2 to R2, we are going R2 to R2. So basis vector for this will be the, we are taking a standard basis. One vector will be the 1 0 and second will be the 0 1. Also for this will be 1 0 and second will be 0 1. So here we can see it. One vector will be the V1, here will be V2, here will be W1, W2, and here element will be come from A1. Here is will be A12, A21, A22, right? So how you will be getting? So obviously we will be using transformation on the V1. Then we will be getting what? A11 W1 plus A21 W2, right? A1 to W2, not V1. If we apply V1 at a 1 0, then how it will be look like 1 0. If we put here 1 0, here 1 0, then we will be getting like 2, 0, and here we will be getting a 1 1, and W1 is nothing but what? This is also 1, 0, and plus here what will be A21 we don't know. So W2 will be what? 0, 1, right? And so from here we can see here what will become A11 will be 2 and A21 will be 1, right? A21 will be 0. A21 will be what? 0, right? A21 will be 0. Now next, applying on transformation on V2. Similarly, that will be what? That will be the whole A12 into W1 plus A22 into W2. And similarly, if we put V2 as 0, 1, then what will we be getting? We will be getting here 0, 1. That will be the A12. There will be A10 plus A22. What will be here? A22. There will be 0, 1. Now we will be getting that thing. So what will be the A12? A12 will be 0 and A22 will be 1. So here we can see it. The matrix form will be what? 2, 0 and 0, 1. This is the way here we can find a matrix from for a linear transformation. This is all the way, right? Okay, thank you.